So we're going to start talking about momentum and impulse to kick off this momentum unit. And to start off with, the concept of momentum itself is just to say that it is inertia with velocity. The equation for momentum is very simple, very straightforward. It is mass times velocity. The letter P, some folks have different reasons. They think why it starts why the letter P is used to indicate momentum. One is M is already taken by mass. Also, I've heard that the Latin petere means to continue or to seek. And so, I don't know. Look it up if you feel like. And so, P stands for momentum. I always think of it as just, it's fun to put a silent P in front of words. So, momentum. That's how you can remember it. At any rate, it's a pretty simple formula. It's mass times velocity. The more mass a thing has, the more momentum it has. The greater its velocity, the more momentum it has. In a way, it's like inertia, but when we add in this velocity or multiplied by velocity, it gives us a sense of what it's going to take to stop an object were it to collide with something else. And that's kind of the whole point of looking at momentum, is wondering what happens in collisions and allowing us to make predictions and learn more about how collisions work. So now the question is, if an object has momentum, what happens if you try to change an object's momentum? Well, if in order to change an object's momentum, it's mass times velocity, it's going to have to undergo a change in velocity. And of course, anytime a change in velocity occurs, a change in velocity over some time, that's an acceleration, and that is going to require a force. So forces are going to cause changes in velocity. And so the way it works out is that there is a quantity that is given the name of impulse, which I really don't have an answer for this, is a capital letter J. But impulse is the change in momentum. Specifically, we could say that the impulse is the change in momentum, which could be indicated as the mass times the change in velocity. It could be just indicated as the change in mass times velocity. It could be indicated as momentum final minus momentum original. Any of those work. They're all equally valid. And so one question we could ask is, that is of interest in this circumstance, is how we're going to change our momentum. Is it going to be quick or gradual? And so the change in momentum can be accomplished by exerting a force for some amount of time. And that is the change in momentum, or that is the impulse, which will be equivalent to the change in momentum, m delta v. So imagine, for example, you're in a vehicle going 10 meters per second. You've got a velocity of 10 meters per second and a mass of, let's use easy numbers, 1,000 kilograms. So the momentum your vehicle has is going to be mass times velocity, which would be 10 times 1,000, 10,000 kilogram meters per second. It is not an elegant unit. It's just the mass, the units of mass multiplied by the units of velocity. And in this example, we're going to lose all of this momentum. So our original momentum is going to be 10,000 kilogram meters per second, and our final velocity is going to be 0. We're going to bring this car to rest. So the final momentum is going to be 0 kilograms meters per second, momentum original, to momentum final. So we're going to lose all of this momentum. Now the question is, how do we do that? Well, we've got choices as vehicle operators. You could pay attention. You could see the red light way up ahead. You could gently hit the brakes and allow the car to come to a gentle and controlled stop. And of course, in doing so, you're causing friction force to be exerted on the car due to the contact with the wheels and the ground. And let's say that the time for that deceleration is 10 seconds. All right, well, the force times the time equals momentum final minus momentum initial. So that'll be the force required would be, well, the momentum final is 0. So we're going to have negative 10,000 kilograms meters per second of original momentum being lost divided by 10 seconds. So 10 equals, works out to be a force of 1,000, well, negative 1,000 newtons. 1,000 newtons pushing back on you. Now, another option is you're not paying attention. You're looking down at your phone and you rear end the car in front of you. So if that were to happen, that time of the interaction, the time of that loss of momentum would be much, much smaller. Let's say it was 0.1 seconds. Well, in that case, the force to bring your car to a halt would be, well, you're still losing the same 10,000 units of momentum, but you're going to do so in much less time. And that's going to cause a much, much greater force. 10,000 divided by 0.01, that's going to be, what was that? 2 decimal places. 10,000, that is going to be 1,000,000 newtons. And so we can see one aspect of how this concept of impulse is useful. It will allow us to determine something about the force that's exerted on an object if we know something about how long that force is applied. And so considering this possibility, well, consider the possibility that a force could be exerted for at a constant value for some amount of time. And if so, the force times the time would be the area of this graph. Ooh, spidey senses tingling. Area of a graph means something. Well, if it's a constant force, that's easy. Just multiply force by time. But if we have some interesting function of force, some kind of force that varies in time, the same principle holds in that the impulse is still going to be found by determining the area under the graph, which in calculus terms is the integral. So whether it's a constant force or it's a varying force, the impulse is going to be equal to the integral of the force with respect to time. That's going to give us the change in momentum. Now, if you're thinking this looks somewhat similar to some recent investigations, you're absolutely right. The work done on an object is equal to the integral of the force with respect to position or respect to displacement. And that would give you the change in kinetic energy. Momentum is mass times velocity. Kinetic energy is 1/2 mv squared. So both mass and velocity are involved. We're gaining or losing some quantity. And in this case, we're talking about the momentum being gained or lost. So yeah, that is a very familiar structure, a very familiar way of looking at things. Except now when we're talking about impulse, we're concerned with time changes rather than position changes. So, well, I apologize if the cut is weird, but I actually did want to talk about this because it does have a pretty important point to mention. Suppose we have a ball going in a direction. Let's go a green ball in the direction at 30 meters per second, striking a racket. Here's our racket, our orange handle, and bounces back and reverses direction, moving at 40 meters per second. And we would like to know what forces are exerted on the ball if this impact takes 1/100 of a second, which is actually pretty reasonable for a tennis strike. And tennis balls are about that mass. And so force times time equals the mass times the change in velocity. So the setup is not very difficult. The force is what we're looking for. It's going to be mass times the change in velocity over time. The mass is 0.06. The time is 0.01. And the change in velocity, well, change in velocity is always velocity final minus original. Now it's final velocity. Here's the important part. Velocity is a vector. If this thing is coming into the right and bounces out going to the left, when it's moving to the left, it has a negative velocity. So its final velocity is negative 40, and its initial velocity coming in was 30. So final velocity minus the initial velocity of 30 tells us that the change in velocity was actually negative 70 meters per second. It underwent a change of negative 70 meters per second. It was going positive 30, comes out going negative 40. So the velocity is a negative change. Change in velocity is negative 70 meters per second. So we got 0.06 times negative 70 divided by 100th gives us a force of negative 420 newtons. Of course, the force is negative because that's the direction the racket was swinging. It was going to the left, as indicated in our picture. Now, this impulse, this change in momentum is, well, momentum itself is a vector. And what that means is we can add and subtract these vectors in the way that we do with vectors. And so let's take this ball of 0.1 kilograms in flight horizontally. So that's this incoming arrow, and it moves with a speed of 50 meters per second. It is deflected, and it comes off of the bat, making an angle of 45 degrees with the horizontal. So it's coming off where that angle is 45 degrees. We would like to find the impulse that acts on the ball during its contact for, we don't know how much time. But I guess we're not being asked for either the force or the time. We're being asked simply for the impulse. Well, if I've got angles, I got to be thinking about vectors, and I got to be thinking about vector addition. What I'm going to do is I'm going to rearrange this a little bit. So rather than sort of defining the change in momentum, I'm going to say, well, what if I move the original momentum over to the other side? That would be like saying, well, I'm starting with some original momentum, and then I undergo a change in momentum, which results in some final amount of momentum. So what I'm going to do is I'm going to set this up. Momentum original, change in momentum, final momentum. Add those together. Oh, this is starting to look like something we've seen before. I can break each of these into its magnitude and angle, and in doing so, I will find its x and y components. And so let's see what I know. 0.1 kilograms times 50 meters per second, so that's going to be 5 kilogram meters per second. So it's got 5 units of momentum to the right and none vertically. We would like to know the impulse. Well, that's this whole thing. We would like to know the change in momentum. Well, we'll get there. As a result of this impulse happening, it is going to be moving at 50 meters per second at 45 degrees. So it's still the same mass, and it's going at the same speed, so it's still going to have the same magnitude of momentum, 5. But now it's going at this angle, which I will define relative to the positive x-axis, so that would be 135 degrees. So my x component, the x component of my momentum, is going to be 5 cos 135, negative 5.34, negative, 3.54. And my y component is going to be 3.54. That's wrong spot. So my final momentum is 3.54 units in the x direction and 3.54 units in the y direction. So then the question is, all right, well, how did I get from these values to these values? I basically just got to fill in the missing ones. Well, in basically what this is showing is that it had some positive x momentum, which has changed and reversed its direction. So it's undergone quite a large change in momentum in the x direction. So, what's the missing value here? Well, it would be negative 8.54. 5 minus 8.54 is negative 3.54. And in the y direction, it had none initially, and it has gained some positive y momentum, which is going to be in the amount of 3.54 kilogram meters per second of momentum. So these two components, I'm realizing now these are in the wrong spots. These two components of the change in momentum, these are the two components of the change in momentum. And so I can resolve those into a sort of the answer to my question, which was what is the change in momentum? What is the impulse? So the magnitude of my impulse is going to be negative 8.54 squared plus 3.54 squared. So the magnitude of my impulse will be 9.24 kilogram meters per second at an angle of inverse tan of, let's see, what we got, 8.54 to the left and 3.54 vertically upward. I would like to know this angle at the moment. Inverse tan of 3.54 divided by 8.54 gives me an angle of 22.5 degrees. 22.5 degrees north of west. That is the impulse. And our final consideration for impulse is an interesting take on how to approach this. We are not being given the amount of time for the change in velocity for one object, but instead we're given an interesting piece of information. It says rain comes down with a velocity of 15 meters per second and hits the roof of a car. The mass of rain per second that strikes the roof is 0.06 kilograms per second. There's a new unit, mass per second, mass per time. Assuming that the rain comes to rest upon striking the car, find the average force exerted by the rain on the roof. So this is going to require a little insightful rearrangement of the values that we have. We've been saying that force times time equals mass times the change in the velocity, and we would like to know the average force. So if we're going to solve for force, we get force equals mass times the change in velocity over time. But let's just slide that time over a little bit. That is going to be equal to mass per time divided times the change in velocity. Interesting. Kind of like when we're playing around with work. Again, there's some parallels here. When we're playing around with work, we're saying force times distance equals that? Oh, when we were playing around with work and energy, we're saying that power is equal to the change in energy divided by time, and we set that equal to the force times distance over time. And we kind of rearrange things a little bit to say that power equals force times force divided by time over distance. Nope. Force times distance over time, and we'd say that power is equal to force times velocity. So it's not exactly the same rearrangement, but it's a clever rearrangement to solve for an interesting thing, or to look at this from a different point of view. And so that's exactly what's going on here. We are being told that the change in velocity is going from velocity final, which is 0, minus the initial, which is 15. So something initially has a negative velocity, which goes to 0. So it's a positive change. Change in velocity is 15 meters per second. The mass is 0.06. The rate of mass per time hitting the roof of the car is 0.06 kilograms per second. And so the force will simply be 0.06 times 15. Of course, it's an upward force. That makes sense. The car is pushing upwards on the raindrops to stop them from falling. And that works out to about a force of 0.9 newtons. Not a ton of force due to the rain pushing down on the top of your car, but certainly a novel way of looking at how to find a force. And so there we go. We've got, sort of to summarize, we've got some big ideas. We've got the impulse is simply the change in momentum, which is also equivalent to force times time. We're revealing that the integral of force with respect to time is for a varying force over a period of time will tell us the change in momentum. And we are recognizing that because this is a vector, we can do vector addition or vector subtraction as needed if things are moving in one direction and then change the direction. So effectively, we've got two-dimensional motion happening with impulses. And lastly, we've got this interesting take on a mass per time. So if you ever see something like some amount of stuff is happening per second, keep your eyes out for this one. Good. Mass per time times the change in velocity equals the force. So welcome to the kickoff for impulse. It doesn't play a huge role in the big picture, and that's why I kind of went through this pretty quickly, even though this video still ended up being 18 minutes long or something. So good luck to us all, and we'll see you next time.